Recording. So cool guys, today we'll be discussing the Codeforces round 872 that was rated for Div2, and we'll be discussing the problem A, B, C and D1. The difference between D2 and D1 is just of the constraint K, but even if you change K, so the problem actually becomes a lot different. So I'll not be discussing D2. I've not even solved it. So let's get started with the first 4 problems. So the first problem is that they are giving you a palindrome. They are giving you a palindrome, and what they are asking you to do is that you have to print the a subsequence which is not a palindrome, right? Now I won't even solve it on the iPad because it's pretty simple. So the simple logic over here is that if you're having a word, right, and it is a palindrome, then it's always possible to remove one of the characters and make it a non-palindrome, right? The only condition wherein this won't satisfy is when all the characters are similar, right? So you just have to check for that. That is, if all the characters are similar, for example over here all the characters are similar, then you print a -1. If all the characters are not similar, in that case you just print size -1. So if you want to see the code is pretty straightforward. Here's the code. So you can actually do it in a far easier manner. You can actually take a set char int over here, and for this you so you can say and s.end, and instead of doing all of this work you could have simply said over here, yeah, anyone saying something? So it would have, if the size is greater than 1, right, in that case the answer would definitely be s.size -1, else the answer would be -1. So this should have worked, I think. Let's try this out. Okay, it's failing. What did we do wrong over here? Weird. Oh, 3, 7, that's fine. 3, 1, that's actually fine. Okay, let's take it like this. Bro, someone's mic is on. Can you please turn your mic off? Else I'll have to turn your mic off myself. Okay, give me a second. Yep, works. So cool. Yeah, this is a solution for this. Yeah, just wanted to show you a shorter code so that it's easier for you to write it in a contest as well. So if I submit it, it would get submitted without any problems. Okay, there's some problem submitting the code as well. Never mind, but I hope you understood the logic and how to code it in a shorter code, right? Just to get the same results via coding less number of lines. So yeah, it's get submitted. Let's start with the problem B now. So the problem B is I don't know, like this name is pretty confusing, but the problem basically states that you are given n into m integers. Now you need to arrange these n into m integers in n rows and m columns. Now there's a condition to it. Now what would happen is that when we arrange these numbers, so let's say this is the table that gets created. It has some n columns and maybe like m rows. N and m are interchangeable because we can, we can change the way we are writing the elements, right? Now it has several, now if I pick the topmost point that is right over here, then I'll get several rectangles, right? So, sorry, yeah, this would be a rectangle for me. So this would also be a rectangle, right? If I change the color, then basically picking this point always has to be there, right? And if I pick up any other point on this entire rectangle, for example, let's say I picked this particular point, right? So this entire thing would be represented by a rectangle. Now in all these cells, so over here there are total of 9 cells, 3 into 3 cells, right? There would be a maximum and there would be a minimum, right? So we have to do maximum minus minimum, and we had to give the sum of this value for all the rectangles possible. So technically how many rectangles would be possible? So in total there would be n into m rectangles possible, right? So for all of these n into m rectangles, we had to give the sum of we had to provide the sum of maximum minus minimum. But now what we need to do is we need to maximize this particular sum. So in order to maximize this sum, what we can do is that we can either place the maximum element over here. So we can place maximum element over here, right? Now the benefit of this is that whichever rectangle I'm going to consider, right? Because this point is always going to be in that particular rectangle, hence my maximum is always going to be there. So this value is maximized, right? Maximized. Now where should I place my minimum? Now there are 2 points where I can place the minimum. So either I can place it over here or over here. The reason being that for this particular rectangle, right, this particular minimum would be utilized. However, when I'll be considering any other rectangle, right, or for this particular rectangles, this rectangle, this and this one, this particular minimum, let's call this minimum 2, let's call this minimum 1, right? So these would be utilized for these rectangles. However, when I'll be constructing any other rectangle for that matter, for example, this one or this one or this one, right, then the minimum of these two would be considered as the minimum, right? So should minimum 1 be less than minimum 2 or not? That would actually depend if your m is greater than or equal to n, right? Because if your n, so over here, if your n is greater, right, then you would want that your mn1 is greater so that the number of rectangles that it contributes to is more, right? So that's how you need to do it. Now there's another configuration possible as well. So you might say that, okay, this is one configuration, but the other possible scenario is that instead of, okay, let's draw it over here. So another possible scenario is that instead of putting a maximum over here, we can put a minimum. Yes, we can do that as well. And in that case, there would be mx1, that is maximum 1, and maximum 2 over here. So I hope this is clear and most of you had already done it. So anyway, if I go to the code, so this is the code for the same problem. So firstly, I'm sorting the elements. I could have also just taken the maximum element and the minimum element out of it, but over here I just sorted it. Then it took the maximum element. So maximum would be at the back, right? Then the minimum 1 and minimum 2. I also checked if my m is greater than n, right? And now I want that my m is smaller because I want that the minimum present at m is used for less number of rectangles. If that's the case, then I'm swapping it, right? Then my result 1 would be, now result 1 basically means that the 0, 0 location has maximum, right? So result 1 would be for this entire rectangle that would start from, okay, let's mark it like this. Okay, let's mark it like this 0, 0. The next position would be 0, 1, right? The next position would be 0, 2 and so on, right? So till the time you reach 0 m. So for this particular rectangle, for all these rectangles, how many rectangles would be there? In total, m-1 rectangle would be there because this won't be considered. Because for this rectangle, the minimum maximum value is same. So there's no point considering this. But there would be m-1 rectangles for which the maximum value would be mx and the minimum value would be mn2, right? And they are m-1 rectangles. So their contribution in totality would be m-1 into mx into mn-2. Now, what about the remaining rectangles? So in total, there were m into n rectangles. And we already talked about the m rectangles in totality. So the remaining is m into n minus m. For them, the minimum number, that is mn1, would be considered, right? So this is res 1. Now what about res 2? Now this is considering that the minimum is at 0, 0, right? If the minimum is at 0, 0, then the element just to the right of it and just to the bottom of it would be the maximum ones. So we'll do the exactly same operation over here as well. And whatever value I'm getting the minimum, if it's in res 1, I'll print res 1. If it's in res 2, I'll print res 2. Cool. I hope this is also clear. Any doubts on this? Yeah, sure, bro. You could have actually spoken up. I kind of forget to, maximize the screen. John, we'll take this kind of questions later on. Cool. I hope you don't have any doubts. If you have, then let me know. Okay, let's move to the next problem. That is problem C. So problem C is over here. Yep. So again, I'm not gonna read the name, but the problem basically states that there are 3 kind of people, right? So there's a large gathering and you have chairs that are placed adjacent to one another. So let me just draw it over here. Okay, so like this, this is the row where chairs are placed, right? So there are m chairs in total and there are n people. Now each of these people have some preference. So either their preference could be that their preference could be 1 or 2. 1 is actually denoted by -1, 2 is actually denoted by -2, or they could have a preference of being seated on a particular chair. So this is chair 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe, right? Now one person could say that, okay, I want to get seated on a chair 7. So you'll have to get this person seated on this particular chair, right? Now what about 1? The person with the level, with the value 1 or the preference 1 would actually say that I want to get seated leftmost. So he'll pick a person who's already present in this particular arrangement, right? So let's say this particular chair was already being occupied, right? And this is the leftmost chair that is occupied. That means there could be some chair that is occupied to its right, but there cannot be any chair that's occupied to its left. So this is not valid. This is not valid, right? Cool. So he'll pick the leftmost occupied chair and he'll get seated to the left of it. Cool. So this is what 1 does. Now what would happen if the leftmost person, or if the chair 1 is occupied, then he'll say, okay, the leftmost chair occupied is the chair 1 and there's no chair left to it. So I can't sit. So he won't be able to sit. And what would happen in case no chair is already allocated, right? So in case it's all blank, then the person with preference 1 would get seated over here. Cool. That is at the extreme right. Now the person with the preference 2 is exactly opposite. What he wants to do is that he wants to get seated to the right of the rightmost chair, right? So let's say this was not filled up right now, and this is maybe, okay, sorry. This is maybe filled up, right? So what would happen is that he'll come and he'll try to sit over here. So the rightmost person and the right chair to the rightmost person is what he tries to sit at. And what about this kind of a person who specifies the chair number? You'll have to make him seated to whatever chair he specifies, else if the chair is already occupied, then he leaves. Now you have a choice of reordering them. So you can say that, okay, maybe like the ith person is going to go first, then I+1 would go, and so on and so forth. That's completely up to you. But you have to maximize the number of people that get seated at the last. So how would you do it? Now the basic approach over here can be that you can say that, okay, if I start with a person who is the leftmost, right? Or whose preference is actually going to the left, which is denoted by 1 over here, right? So what would actually happen is that, let's say this is your entire seating arrangement. Now he'll see that, okay, no chair is already occupied. So he'll go and occupy the last chair, right? That is the rightmost chair. That's fine. And it actually doesn't matter much, because even after it, let's say another person with the same preference comes. So another person with preference 1 comes, then he can sit over here, then other can sit over here, then other can sit over here, and so on and so forth. So it kind of looks like a nice pattern, right? The only problem is that now if a person with the priority right comes, so he cannot sit anywhere, right? Because you already occupied the rightmost chair. Now similarly, if you start with the right, or you start with a person who's having a preference 2, in that case, he'll sit to the leftmost place, right? Because all the chairs are empty. Now, this is also fine. You can accommodate any number of people having the same preference, right? They'll keep sitting to the right of it, but you cannot accommodate even a single person having preference 1. So these are the two base cases. So if you start with any left or any right, in that case, you cannot accommodate the the person having the exactly opposite preference. Or if you accommodate 1, then you cannot accommodate 2. If you accommodate 2, you cannot accommodate 1. However, there's a catch. Now let's say I didn't start with L or R. I rather started with any person who was having a particular preference. So maybe there was a person who wanted to sit at a chair X, right? And let's say this was the X chair. So I get him seated over here. Now if a left comes, so I can get the left seated over here. Right, let's denote left by red color, right? So left would get seated over here, then he can get seated over here, and so on and so forth, right? Now let's say if a right come, then also he can get seated over here, he can get seated over here, and so on and so forth. So this sounds to be a better strategy. But the point is, which X are you going to start from? So there's no perfect choice over here. So we'll have to try for all the possible X's. Now what you need to understand is that when you choose a person who's having such a preference that he can he'll choose a chair and he'll sit at it, right? Then all the people that were having similar preferences. So all the people who wanted to select a chair, right, and they are having a preference that is less than x. So it could be that let's say x is equal to 8, so he wanted to sit at 8th chair. Now there could be a person who wanted to sit at the 6th chair, or maybe x is equal to 2, or not, let's not call it let's call it y or z, right? So there could be a person who wanted to sit at the 6th chair or the 2nd chair, right? So these people would be later accommodated, right? But when you calculate in totality, so you'll say in this particular range, that is from 0 to x, how many people do you have that you need to get seated? So the total number of people that you need to get seated are the people with the preference 1, that is who want to get seated to the left, and the number of people who are having the preference 3, that is a fixed chair, but for whom the value of the preference is less than x, right? And how many people do you want to get seated over here? So over here the number of people would be r, that is the number of people having the preference 2, plus the number of people having the preference 3, that is a fixed chair, but over here the, let's say, the preference should be greater than x. Cool. So this is about that. I'll explain the code and this would become more clear. But any doubts in this so far? Okay, I'm assuming things are going fine. So yeah, cool. Let's move to the code now. So this is the code. Now what we're doing in the code is, firstly, they have said that okay, the people with the preference 1 are represented by -1 and the people with the preference 2 are represented by -2. So we'll iterate through all of this, right? And if we are getting -1, so we'll say okay, there's a person with the preference left. If we are getting -2, then there's a person with the preference right, and else, so there would be a person, right, who want a specific chair. And we'll push it on a set. Now why set? Because set actually gives me values in sorted form. Also, now let's say there were 2 people who were fighting for the same chair. So 2 people wanted to sit at a 6th chair. There's no we can accommodate 2 people at the same chair, right? So only 1 vote should be counted and the other person has to be thrown out. And it's also, unique elements. So the duplicates are avoided. That's why I'm using a set over here. After that, I'm assuming that I started, if I start with a left or a right person, right? In that case, if I start with the right person, I cannot accommodate any left person or vice versa. So the answer would be minimum of m, because you cannot exceed m, where m is the number of chairs you are having, or maximum of L plus. So L is the number of people having the left preference plus the number of people who want to sit at a chair, right? And then R plus the number of people who want to sit at the chair. Whatever the maximum value would be, you can store that in rest, because this would be the case when you don't start yourself with a person who's having a fixed who's having a preference that is 3. So you don't start with a person with the preference equal to 3, but you start with either left or right. Cool. After that, I've taken size, that is basically the number of people having the preference 3. Now I have studied left. I could have used a better variable, but this is what I coded for the contest. And left basically means, so when I'll be traversing through all these people having preference 3, so since this is already sorted, and if I'm at the ith person, so that means all the people who are having a preference 3 and who wanted to get seated as chair that is less than x would already be traversed. I wanted to keep a check of them, so left is being used over here, right? Then I say that if I select this particular person, so okay, if x person is selected, right, x is selected, in that case what would happen is that there would be, okay, over here I'm saying I, so yeah, if ith person is selected, then I minus 1 chairs would be to the left of it, right? So to the left of it, there are I minus 1 chairs. I can utilize them. How many people do I want to get seated over here? Over there I want to get seated L plus left people. Now what is left? Left is the number of people with the preference 3 that I've already computed, and L is the number of people having a left preference, plus minimum of how many chairs are there to the right of it. They are m minus 1. So m minus 1 plus r plus, now size minus left, if I do, okay, yeah, size minus left minus 1. What does this denote? Now size minus left minus 1 is the number of people having a preference 3, but those are to the right of it. But why I'm doing a minus 1? Because even this particular person would actually be would not be counted, right? Because we are sure that we are gonna include this particular person, and hence I've done a +1 over here, and then I left plus plus so as to so as to denote that we have already traversed one person, and at the end we'll print rest. So if we run it, this works fine. Cool. Any doubts in this? Okay, gonna move to the next question now. Let's go to the problem D1. This is a good problem. Okay, so the problem states that okay, I'll not go through the problem because it's a bit long. But anyway, what we need to do is that just try to understand it like a graph. So they have given us a graph, not a graph, just a tree, right? So it's a tree which they have given us. Now we have to select k nodes at random. So any k nodes can be selected, but k can only go up to 3. Cool. So after selecting k nodes, so k could be 1, 2 or 3. After selecting k nodes, we want to select another node, let's say x. Now x can be one of these nodes or not, but the value of x should be such that the distance, if we sum the distance of going from x to all these k nodes, this should be minimized. So the sum of distance of x to all of k, okay, should be minimized. Now, important observation over here is if my k is equal to 1, that would basically mean I'm just selecting a single node. So if I select this node, if I select this node, then what is the node which is having a minimum distance from this point, right? So obviously this node itself. So I don't have any other choice rather than pointing this node itself. Correct. What if my x is this? Then I'll have to pick this particular node. Now this thing changes a bit when k is equal to 2. Now let's say this is the graph I was having, or the tree I'm having, right? Now let's say this is a k, correct? And this is another k. So this is a node that I need to go to, and this is a node I need to go to. Now, what all nodes can be utilized over here? So let's say what would be the answer if I select this particular node? If I select this particular node, then this node is at a distance 1. This node is at a distance 1. So 1 plus 1 is equal to 2. If I select this particular node, then I'll have, so 0 distance is required to go from the same node to the same node. That's fine. But 2 hops would be required to go to the next node. So that would be 2. So 0 plus 2 is also equal to 2. What about this? Over here also the answer would be 2 itself. So technically I have 3 nodes that can be utilized now, right? So when your k is equal to 1, the answer always would be 1, because you have to select the same node at which the person is placed, or which you need to go to, right? However, when your k is 2, the answer can vary. What if your k is equal to 3? Now I can prove it mathematically, but it's not required. It's intuitive. So let's say this kind of a scenario is there, right? And you can imagine any scenario. So what would actually happen is that there would be some kind of unevenness. What do I mean by that? Now, in case there was this branch chain structure, right? In that case, if you are having 2 nodes over here that are colored, right, and 1 node over here that's colored, or the nodes you want to visit to, even in that case, there would be only one perfect answer, because as soon as you move your vertex, so let's say this is the vertex you selected, this is the node you selected, right? So as soon as you move your node, so what would happen is, if these are the 2 nodes that were selected, so if you move your node over here, then this would incur a +2 distance, right? And this would incur a -1 distance, because you're coming closer to it. So over here, you will be coming closer to it, but you will be moving away from these, right? So basically this would become a +1. You don't want to do that, right? You want to minimize your answers, hence you cannot operate over here. So basically for n is equal to 3 or n is equal to 1, the answer always is 1. For k is equal to 2, we need to see that what the answer would be. Now how can I come up with this? Because I cannot brute force it up, because there would be many combinations. I cannot check for all the combinations. I need to do it in a linear order. How can I do it? What I can rather do is, I can stand at a particular node, right? I just need to know from this particular node how many branches go out. Cool. Now let's say this is a particular child of it, right? when would this particular node not be a good node? In what scenario this node won't be a good node? By good node, I mean that the distance of going from this node to all to the other node is minimum. When would this not be a good node? In case there's a node I need to visit over here and there's a node I need to visit over here, then obviously it's a good node, right? So basically, if this node X comes in the path, if this node X comes in the path where which I need to traverse to go from one of the colored node to the other colored node, then it would be valid. But in case it doesn't comes in the path, then it won't be valid. So when won't it come in the path? That would only happen in case all the colored nodes are actually from a single child itself, right? So how so we can do one thing over here. We can take all combinations minus the bad combinations. That would give us a good combination, right? So bad combination basically would over here be that in a single child itself you are having all the colored nodes, right? Or basically over here k is equal to 2. So you are having both the colored nodes in a single child. So you can say that, okay, so you can either do nc2 or you can basically do n into n minus 1 divided by 2. It's completely your choice. And actually this converts to this, but never mind. Okay, so so that's what you need to do. You'll stand at a particular node. You'll get the count of its children from each of its edge. For example, if this is your tree, right? If this is your tree, then standing over here, you'll say that, okay, let's make it a bit bigger. So you'll say that, okay, 3 nodes are over here in this subtree, 2 nodes are in this subtree, and 2 nodes are here in this subtree, right? So 2, 3, this is a value that your children are going to return you, 2, 3 and 2, right? And then you will have to compute that how many possibilities are there that a single child would become would present a bad situation to me, and it would be a bad combination per se, and you'll have to subtract them. If it's not being that clear, maybe you'll have to write it down again and try to understand it. But when I'll explain the code, maybe this would become more clear to you. So if I jump to the code, okay, I don't know why it's getting highlighted. Okay, it's cool now. Okay, so firstly, I've actually made factorials and stuff because I was doing it in a different fashion. It's not required. You can just do n into n minus 1 by 2 for calculating the bad permutations. But anyway, so firstly, we'll take the graph inputs. And I wanted to start with a leaf. You can do it without a leaf as well. It actually doesn't matter, but I did it with a leaf. So here I'm taking a leaf and I'm checking if k is not equal to 2. So if my k is either 1 or if it's either 3, in both of the cases, the answer is 1. So I'll be doing that. Else I'll start this DFS traversal. Now what this DFS traversal is doing, that it's a basic DFS traversal, right? So it will just get me the count of number of children in a particular subtree of its, right? So it will check for the subtree that is starting at the root ch, right? And then it will say that if your v is greater than or equal to k. Now if your subtree has more than equal to k nodes or greater than or equal to 2 nodes, only in that case you can utilize, you can have both the nodes in that particular subtree or both the colored nodes in that particular subtree, right? In that case, your bad count increases by n into n minus 1 by 2 or ncr v comma k. You can use anything you want, right? Over here, I'm using ncr because earlier I was using a different logic and then I changed it, so I didn't change ncr and all that stuff, right? And then what would happen is, so for now you traverse through all the children, right? But now let's say you started somewhere over here. Okay, so you are over here. These are the children. So you checked for this, you checked for this, right? And you got that the total count of your children is also 5. But now there is a parent to you, this particular thing, right? You have to also calculate that. So how would you calculate that? You can simply say n minus count of children minus 1. That would be this particular subtree. So you also have to calculate for that. So that is something I'm doing over here. So parent basically is n minus, n is the total number of nodes minus the number of nodes in your child minus 1. And then I'll check if my parent count is greater than or equal to k. Then I'll have to check that all the k nodes or all these colored nodes or k nodes should not be in that particular subtree, right? So similarly ncr parent comma k or parent comma 2. And then what I'll do is the number of good nodes would be total number of nodes, that is nc2 or nck minus bad plus mod. So this is the basic way of taking a mod, because when you're subtracting you just have to add the mod as well. Then the final answer would get incremented by the good number of combinations, right? And then you'll return the child count, but before returning it you'll add a 1 to it so as to denote the self presence of the presence of the current node. And while printing the answer, they had specified that if you're getting an answer in p comma q, then p divided by q, then you have to take a mod inverse. So the denominator over here is the total number of combinations. The total number of combinations over here is basically using any k nodes from that entire subset, right? So it's NCR n comma k, or using any k nodes from that entire tree. So that's NCR n comma k. So yeah, you'll do that. You'll take a mod and you'll print the answer. Cool. So that's it for this. I hope you guys understood. Less people left. I guess this question was a bit difficult, but cool. I'll stop the recording.